So we want to start off this unit by talking about work. Work occurs when we have a force and a displacement. So in order to have work be done, we need to have a push or pull on an object, and that object also needs to move. Now, one key component to work is the direction that we apply the force. Let's say we have a floor here. We're trying to push a box across the floor. If we're pushing down at an angle, but the box's motion is this direction, not all of that force is causing the box to move in this direction. Okay. What we want is just the part of the force that is causing this motion in this direction. So to do that, we can do it with our equation, and we can say that work is equal to force times distance times the cosine of the angle that we're pushing at. For example, if we look at our picture here, let me take a little bit closer look. The angle that we would have, right, since we're talking about the cosine here, we're talking about, either this angle here or this angle, either one that gets us this component of our force. So if we bring our picture back here, this is going to be our general equation for work. Work is a force applied over a distance, and we're taking only the component of the force that is in line with the motion. Don't overthink the cosine part here. If you're given an angle in the problem, that's the angle you're using in this cosine piece. One important piece to this to note is the units for work. Okay, so our units here, if we have a force, well, a force is a Newton, and distances are measured in meters. So you have a Newton times a meter, and a Newton times a meter is a joule. If we split up a Newton a little bit more, if you remember from our last chapter, mass times acceleration gave us a force. So kilogram meter per second squared times a meter gave us a joule. So a joule is a kilogram times a meter squared, okay, those two together, over a second squared. So now we want to talk a little bit about the work kinetic energy theorem. The work kinetic energy theorem goes something like this, in that if we're applying a force over a distance, so work equals force times distance. I'm going to ignore the cosine theta part here and assume that we're pushing in the same direction as our motion. So that would mean that cosine of theta is just 1. So we get just force times distance. So we talk about force times distance. Well, we know from last chapter that a force was equal to mass times acceleration. So let's take that and plug it in for force. So mass times acceleration times the displacement or distance that we move. Now we're going to take one of our old kinematic equations and rearrange it. V squared equals V naught squared plus 2a delta x, or maybe d in this case, right, how far we've gone, and solve for a. So when I do that, I get a equals v squared minus v naught squared over 2d. Then I'm going to take this expression and plug it in here for a. So I get work equals mass times v squared minus v naught squared over 2d times d. So my d's are going to cancel out. And I get work equals, if I do a little bit of rearranging here, 1/2 mv squared minus 1/2 mv naught squared. This expression right here is our work kinetic energy theorem. Kinetic energy is the energy of motion and is equal to 1/2 mv squared. So you can see where the name comes from now. So that's kinetic energy. So work for us is going to cause a change in kinetic energy, right? So this is our expression for kinetic energy, and this would be like kinetic energy final minus kinetic energy initial. So it's a change in energy. So work, another way to write it maybe would be that work is equal to a change in kinetic energy, which should make sense to us, right? By pushing on something with a force, we're going to cause it to accelerate and speed up. If we cause it to accelerate, we're going to change velocity. And if kinetic energy depends on velocity, then by changing velocity, we're changing kinetic energy. So you can kind of follow that chain down and realize that if we do work on an object, we're going to cause some sort of change in kinetic energy. So let's take just a quick minute to look at kinetic energy. All right, kinetic energy we said was 1/2 mv squared. A couple important things to note here. First, and most importantly, is the squared here on the velocity. So that means when it comes to kinetic energy, what matters most with kinetic energy is velocity. Right? A change in velocity is going to give me a much bigger change in kinetic energy than a change in mass will. For example, let's say I do 2 times my velocity. So my velocity is doubled. Well, if I do 2 times my velocity, 2 squared is going to give me 4. And so this is, if I double my velocity, I get 4 times the kinetic energy. If I were to triple my velocity, I get 9 times, right, because of this squared here. Whereas if I double, so 2 times my mass, well, mass is just mass. There's no squared or anything in the equation. So that's just 2 times my kinetic energy if I double my mass. So by doubling my velocity, I can actually get a lot more kinetic energy out of it than if I just doubled mass. Kinetic energy also has units of a joule. Right, if we go for units for kinetic energy, okay, we have 1/2 mv squared. That 1/2 we can kind of ignore. Mass in kilograms, velocity is meters per second, which is squared. So that's a kilogram meter squared per second squared, which was equivalent to a joule. So kinetic energy is measured in joules, which should make sense, right? If work was a way of changing, of giving something or taking away kinetic energy of something, then joules would be our unit to use. And that's going to be our unit for every type of energy that we have. So now we want to look at gravitational potential energy. Gravitational potential energy is another type of energy that we have along with kinetic energy. Where we get this, for example, is if we took a little ball here and it started out on the ground, and then we took that ball and we lifted it up in the air some distance. So let's say we lifted it up a distance of 5 meters. We've given it what we call gravitational potential energy. And that's because at some point, if we let go of this ball, it could fall down and gain kinetic energy, right? It'd have kinetic energy near the bottom because of its motion. So gravitational potential energy is a type of energy, and it's a potential energy, which means it's energy that the object doesn't have or isn't using right at the moment, but it does have, and that it can use and can be transformed into another type of energy. Gravitational potential energy involves a couple different things. Mass matters when it comes to gravitational potential energy. The heavier an object is that we lift up, the more potential energy it's going to have. The more mass it has, the more energy it's going to have. Gravity matters because it's gravitational potential energy, and that acceleration that it has as it falls is due to the gravity of the Earth, or g, and it matters how far we lift it, right? The higher we lift it, the more potential energy it's going to have. So our equation for gravitational potential energy is mass times gravity times height. Just double check and make sure units work out here. We have kilograms times our acceleration of gravity, meters per second squared, times our height in meters. And we get kilograms meters squared per second squared again, which is a joule. Right? Not quite as complicated as kinetic energy. If I double height or double mass, I'm doubling my potential energy. There's no squares or anything that we have to worry about here. So there's a couple different types of energy, and we can kind of see how work factors into it. Work, remember, is our way of giving or taking energy from things. So work could make an object move by giving it kinetic energy. I can also do work by lifting up an object. If I apply a force on an object to lift it and then stop it up here, I've used work to give it gravitational potential energy. So remember that work is always our way of giving or taking energy out of any given system or out of an object.